Okay, now let's see if that's going to be this one, because eight two oh seven. Ah, so you are Joel. And let me see. I want to do that. Can you hear me?
Yes.
Yes, no?
Yes.
Okay. And this is the same one. Yeah. Let me see. That's gonna be a problem. Still a problem.
I did not know that. Oh, this one's on. Are they on? I want to say hi.
Well, Joel is.
Oh, that's
Actually, it's Lewis. Now, the problem is,
hi, Lois. Hi.
Hi.
I hear me on this.
Oh.
I've got both of them on. The top one is that one. And I got to figure out how to,
Oh, there's two. There's two of us.
can y'all tell me how I could get that to not hear the
Louis,
mic?
do you know?
Because I want to be able to share the screen from this one.
Wait, so what's the question?
I want to get my laptop to not,
Just mute it.
I did.
Oh. Just turn the volume down.
Well, it's muted.
What's up, Kate?
See, I get feedback.
What if you turn the volume down
I did.
all the way? No, it's still gonna echo.
It's because they're like close to each other that it does that.
But I can't share my screen without it being over
We
there.
need that one off.
Mute this one?
No, but we just need that to go away.
But then I won't be able to share from that screen.
How did you do it with me?
I think I just had this one on.
Oh, you want to share? Oh, okay.
Let's see what this is.
That's fine.
It's nice to say that you have.
That's not it. Switch to active speaker.
I was like, what is that?
If I'm
I can't hear anything anymore.
not,
This is gonna be interesting.
Look, we're in a diagram. Oh my gosh. Guys, look.
a host disabled screen
Actually,
sharing. Okay,
I
I
am
need to
gonna
go to
watch it.
settings.
Just touch on basketball.
And
We'll do that. Guys, it just might be the three of us. Okay.
retrieve.
Password protected. Oh, guys. I never got to stand on it because I was hurt. I really want to stand on it now. Do it. Here's Catherine. I got my letter back for the patch one. And you know the emblem that you have by your name? You know this one? It's
Yeah.
here. Where am I standing?
Wait, okay.
Depends on where you stand.
So where do we need to be?
You're in a little. Wait, no, I'll figure out. It's still not working.
Wait. This is like the pontoon boat. Did y'all do that?
Not this one. But we did like.
We did that, the priest did that.
Hmm. Okay, I don't know if this is gonna work.
But wait, we go to, no,
There. Whew.
yes. Okay.
Come on.
Yes.
It's looking for me.
Oh my
Oh,
god.
we almost got.
Over here. There it is. I thought I'd let him join. So what are y'all figuring out?
Trying to
We're trying
balance
to
it.
balance each other.
Whoa.
Oh gosh. Sorry.
You know what else I didn't get to do?
I didn't get to balance the ruler.
Uh,
Oh, no, I forgot.
Yeah, I didn't think you could do anything, guys.
Because you were limping around,
Yes, I was on crutches.
and I think I put all that equipment up. The STEM class needed it.
Wait, Mrs. Belcher, Mrs. Belcher,
Oh man, my south center's like on that side of the roll. I can't get in the middle.
I'm my first official fourth practice.
Kayla had hers earlier though.
Well, yeah, but I was out the week before.
Oh,
So
yeah.
like, and plus so was Hackerson.
How was it?
It was pretty good actually.
Oh, yeah. I was in that.
This is the only middle that will never play right side. Because they can't play right.
Why not?
Because they think of it. They can't hit over. I can't do that. We were running sides though. We'll keep them.
That's literally the right side. That's literally the
I
right
know, but that's like a different thing.
We didn't have one right right.
Hey, don't.
But I'm not doing anything.
Oh,
I'm like,
okay,
stand up.
No. I love him.
where's my you?
You should go say hi.
I think he's in the freshman room.
Oh my god. Okay.
So many people that are like,
Okay, so where did everybody go? Take roll, this is physics. Anybody, let me know if y'all notice anybody entering. It should make a sound and I may not hear it. And I can let Ava and Brian in. Kylie? Okay, because Kylie's not, I don't think. Okay, so present. We don't have Ava yet. Madison, Cameron, not yet.
Oh, Cameron, yeah.
Yeah, she's gonna be,
Lewis got here early. He got here.
yeah, he was here.
Lewis here. Lewis.
Yes, I can hear you.
You have to,
Lewis.
Can you all hear me?
there we
Brian's
go.
there.
Brian.
Oh.
Ignore him.
No, block him. Block him. Oh, I missed it.
Okay. Well, did he show up?
He's on thoughts. He's there.
Waiting room, no, joining, okay. I should have Cameron and Ava too.
Did she just call for this? Didn't she test?
No, she was up for this.
Hi, guys.
I know, right?
I was sitting there literally last night.
I mean, I'm literally lost in my paper right now. I don't know where to begin.
I literally know how to do it.
Wait, what?
Oh, we were working on it.
I did one confirmatio. It's terrible, but we'll fix it because we'll fix it.
Has anybody heard from Cameron?
She's not coming.
Is she absent or
Brian, you can't see y'all.
does she want
She
to?
was gonna do virtual.
Okay, well, I'm waiting for her to see if she joins in then. So I got Catherine, Jason, Brian, Kate, Sierra.
Oh, Cameron is right there.
Oh, yeah, let her in.
Wait, is Ava doing virtual too?
So 1, 2, 3, 4, 5, 6, 7, 8. And that leaves Ava. Yeah. I hope Ava doesn't come to school because I took her parking place.
Oh, it's not. I was like, no, they have no mercy.
Don't tell.
They heard they weren't coming and they're like, okay.
Cameron, Cameron.
There she is. Hey. Oh, here, let me go over here so they can see you.
Hi, guys.
I don't know if they can. Wait, am I even in the picture? Oh, there I am.
This is awesome.
Yeah, this is great.
Okay, now you see this little thing right here? It's a mic.
What? Wait, what does that mean?
Oh, that
I'm
was a
scared.
mistake. To
And here's a mic over here too.
Wait, hold on. What does that mean?
They can hear it.
Oh my gosh. Okay, guys.
They've been listening to you the whole time.
They would love that.
Let me go get my book. Okay. I looked at the announcements and there was nothing new. Everybody turned in their phone, wear your mask in the hall.
They're watching me. Wait, hold on. The camera's not projected right there.
No, now it's on me.
Okay, cool.
If you can't see him, he can't see you
That's great.
or them. Oh, wrong book. But I gotta get the other book. So not following me. Oh, well.
My back hurts. No, I'm serious though, bro. It hurt. I think I pulled this.
Oh, volleyball. I played volleyball for weeks and they just sent me out there. My parents are like, they're like, I do that.
Yeah, I think I need to get this more centralized. There we go.
Oh my goodness, they can hear us now.
Oh my gosh.
Well, you know, y'all may ask some good questions or may answer. There we go.
We should put like really funny
She said that.
like styrofoam. That's a good idea. Get a plate of bourbon. Ew! Oh my god. It took me a while.
And I'm supposed to take your temperatures. Let me go check with Mrs. Day because my thermometer's not in here now.
Oh, how was your Thanksgiving? Oh. Oh.
Okay.
Oh. I know
I
you
mean, they had a small, it was just the 4 of us.
Okay.
Yeah. Yeah, it was, I went with my grandparents and we sat at different tables and then we dropped out.
And put it in the box.
Which is fine, I got to sit at home and sleep.
We were with 25 people.
Yeah, I heard that actually. Yeah, I heard from Pastor Carter, he was like, oh, we had a big one. And I was like, okay. Okay. We literally, yeah. And he was like, there's not like 40, so this was social distance for us. I was like, okay.
We do what we
That's
do.
normally our big one, is there's about 40 of
Yeah,
us, but
see-
like, it was so many, it's just, it was just like great.
But everybody else is 97.7 and then you jumped up to 98.4, 98.1.
So I was like, I'll just sit
And I
out.
can go boop, 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 boop.
I love these things. Guess what I had for breakfast on Friday, Marie? I had pie.
I think I did too.
And for lunch.
Pecan, right?
No, yes, I did have pecan. I love pecan.
And my mom's birthday was the 28th. And so I got her one of these fudge cookies, like a chocolate chip cookie pie, but it's fudge with icing.
Oh my gosh.
Guys, I think, wow. But okay, you know what I tried at Starbucks? I tried their green matcha.
Oh, the matcha latte, yeah.
It's so good,
Yeah,
guys.
it's
Oh
good,
my
yeah.
gosh, I'm addicted. And I've only had it once.
Okay, well, we'll start with prayer. I'm gonna not worry about the devotional since we're kind of behind a little bit. Any prayer requests? Besides all the, do y'all realize that technically for this week, we're gonna be a girls' school at the Rhetoric?
That's weird.
Well, no, because all the freshman boys are here.
But
Oh. They heard that. Just our class.
But that's like, but at least we're not like drama prone.
That's
so
true,
we're
it's
actually-
Ian, so like, I'm not complaining.
Oh my-
Everybody have good Camp Eagle experiences? Did y'all have good Camp Eagle experiences?
It was so fun.
Me too, I liked it. Okay, so we had Camp Eagle, we had Thanksgiving. Now we got this weirdness.
Mrs. Belcher,
So I'm gonna pray and then we'll get started on chapter 5. We're praying. Dear Jesus, thank you so much for the fellowship that we have here. And I pray that you will just help the students that are virtual and absent, that they will continue to feel part of Annapolis. And I pray that you'll help us to deal with any technical difficulties. I pray that you'll just bless each student here or online and help us to just honor you and to show ourselves as a family with you as the head. In Jesus' name I pray. Amen. Okay, so turn to page 134. And I could pass papers back if y'all want to see your
Mrs.
test.
Belcher.
We took a test? What?
It's been 2 weeks.
It was on the Monday.
Look at all these papers.
Mrs. Belcher.
I got to start using some of my Christmas stickers. Of course, half the people aren't going to get theirs.
Can she even hear me?
I was
like-
gonna
Yeah.
text you, but. Wait, did you turn it in?
Problem.
In that class, I can take it. I don't know what actually.
Why isn't it following me?
I decided last night.
I think y'all lost me. Hang on. There we
Mrs.
go.
Belcher.
All of the Santa stickers. Everything.
Let me see if
No, what were we talking about before?
Ava and Ava both are waiting. Okay.
Never mind. I'm not getting it. Never mind. Oh, and the Kathy?
Okay. Let's see if
We
we
talking
get.
about that. So what you're talking
There
about?
she is. Good morning, Ava. I'm sorry I didn't notice you were there.
Your test?
All we've done is pray so far.
Okay.
I'm passing papers back. I could hold up your tests to the camera,
No, please
but I
don't.
better not.
Yeah.
Catherine.
Brian's like, show my grade. Good.
Thank you.
So we got 5 there.
Oh, Eva's here. Hi, Eva.
Yes. 1, 2, 3, 4, 5, 6, 7. Oh yeah, that's what I mean. Camera. Yeah.
I just think
You're wearing illegal outerwear, young lady. Who else? There, are y'all in dress code? You're supposed to be, technically, just so you know.
What are they gonna do? Come to my house?
I almost forgot to talk.
I guess.
I have so much trauma for forgetting it's chapel that I remember now. It'll be like 3 in the morning and always 2. Bro, I messed up my schedule so bad. Like, a couple days ago, it's gonna be 3:30 in the morning and I was still eating something and I wasn't tired. And I'm sitting there like, I can't do this. Like, this isn't allowed. This is bad. I haven't stayed up past 3 in the morning since like 8:30.
Really?
Yeah. Like, I normally go to bed at like 11 o'clock. I was late, is like midnight. 3:30 in the morning, I was reading a book. And I was just sitting there like, dang, I'm so tired. I finished the book in one sitting.
Hey, that's.
I finished 2 books in one sitting over the course of 3 days.
Was it just like a pleasure read or did
That would be like philosophy.
I'm not sure how to get the papers back to them. They can just get them when they come back to school, I guess.
There's something.
I mean, you probably could change. I mean,
If I write it real.
Any questions on any of the papers I passed back?
and plus, hey, like, the seniors last year, half of them didn't have to until 2 weeks before.
Is that a question for the test? No. Okay, so we're on page 134.
1:30.
It's kind of a very broad topic, energy. Yeah,
That's pretty.
the diagram there. What is that?
It's an ombre.
It's
It's the history of the universe. Everything's right there in one picture.
Oh, look at the big one.
Mhm. Starts with the Big Bang, and then there's a little thing that says "You are here." Just kidding. There's not one. It's you're at the very, very right-hand side.
13.8 billion years.
I know it's a long time. And why are we seeing that picture on the front of this chapter? Hmm?
Because energy.
Which is what? Everything, right? I mean, energy was what started at the Big Bang, and now as it got out to further and further, like let's see, earliest time visible light. I don't know. You started getting matter kind of congealing out of all the energy, but everything is basically mass, energy / time and space. Okay, and so this just pretty much covers everything there is to cover physically. I mean, when it's not covering spiritual stuff and that kind of stuff, but everything in the physical world. And he talks about in the caption down there about how scripture starts with the beginning, God created the heavens and earth. And so he kind of relates that to the Big Bang and the laws of physics and everything. When people don't believe in God, they tend to say that the laws of physics created the universe. But they don't ever answer who created those. So anyway, what we're going to do is in this chapter, we talk kind of a general big picture idea of energy in section 1 and kind of the history. And then in section 2, we'll get into different kinds of energy. And there's several different equations that we'll look at for each kind of energy. Now, does anybody remember what the unit is for energy? Any wild guesses? Joule. I can see Brian. Okay, I can't see Cameron too well. Is she there? Yeah, she's there. Okay. Right, joule is a unit. And so everything that we're going to be looking at in this chapter, we're going to be talking about potential energy and kinetic energy and elastic potential energy and mechanical energy and radiant energy and work and chemical energy, electrical, thermal, internal, nuclear, and acoustic energy. All these are different types of energy, and they're all measured in joules, okay? And heat, they mention heat, and they get more specific about heat further in there. And there is another equation for power, which is the rate of energy. Energy divided by time, The rate of energy is power. So we've been talking about that, and then using all those equations with all the ones you've already been using. I do not think we're going to have much free body diagrams in this chapter, but don't lose it all. So what we're going to do is we're going to read through section 5.1 today. Just, I know it's kind of weird to read through it aloud. If the people at home don't want to listen to them read it, then you can turn your sound off and read it to yourself, or you can listen to these guys, either way. So look on page 136. Energy, matter, and the beginning of the universe. So Maddie, I'll let you get started.
Just a paragraph? Or like-
Let's do the first two paragraphs there.
Okay. Energy is an enormously important topic in physics. A great deal of physics consists of modeling the energy in different types of systems. It seems appropriate to begin this chapter on energy with some comments on the big picture. However, to discuss the big picture about energy at any level of detail would require volumes. Thus, we must be content here with some brief remarks to help contextualize the topics we will address in more detail. One way of describing the physical universe would be to say that energy is the only thing that exists. As we will see later, matter and energy are now regarded as different forms of the same thing. Thus, the term energy and the law of conservation of energy necessarily involve matter as well. When listing the fundamental constituents of the universe, scientists will often mention matter and energy. But as I described back in chapter 3, there is a third constituent, the laws of physics that mathematically govern the operation of the natural world. Every scientist acknowledges that the physical world is governed by physical laws that are expressible in mathematical form. Most scientists also acknowledge that the mathematical structure of nature is ineffably marvelous. Scientists cannot say where these laws came from, but to those of us who worship the Creator, it is obvious where they came from. The laws of physics are the proverbial smoking gun, or fingerprint pointing us to the intelligent designer that brought the universe forth from nothing. This intelligence is now evident in the mathematical structure of the physical world and in the order, patterns, and information that are seen everywhere, from the elliptical orbits of the planets to the instructional content of DNA. So the fundamental constituents of the universe are matter, energy, and intelligence.
Okay, thank you. Catherine, would you pick up there?
Just to the end of the section?
Yeah.
It is not possible to articulate a robust definition of what energy is. We just have to accept the proposition that the physical universe emerged out of the energy that was there at the beginning. In contemporary physics, energy is regarded as a property of objects that can take on different forms, can be converted from one form to another, and is transferable from one object to another.
Okay, can you stop for a second there? So that's as close as we get to a definition of energy, because it's one of those things that's so basic that it's hard to, I mean, that's where you start getting analogies in order to define other things like time. What is time? You know, that's hard to define too. So what he mentions here is where it says it's regarded as a property of objects that can take on different forms, can be converted from one form to another, and is transferable from one object to another. That's kind of the important thing you need to remember. You might have learned a definition previously about energy as the ability to do work. Does that ring a bell? And that's kind of pushing it too, but it's really more broad than that. Okay, so continue on.
These will be the topics we address in this chapter. Since the early 1960s, scientists have been able to develop a detailed theory of how the universe unfolded since its beginning. The current standard model, as it is called, predicts the stages of the early universe as summarized by the graphic on the opening page of this chapter. There were two key discoveries that enabled the formation of this model. The first was the discovery by Edwin Hubble in 1929 of data that strongly implied that the universe is expanding. The second was the accidental discovery in 1964 that the universe is suffused in all directions with a steady level of microwave radiation. This discovery came about by means of the Holmdel-Horn antenna, pictured in figure 5.1. This antenna was designed as a radio telescope, and scientists found that no matter which direction the antenna was pointed, a uniform background of microwave radiation was measured. This background radiation, now known as the cosmic microwave background, is now understood to be the radiant energy left over from the original energy explosion that formed the universe.
Okay, let me interrupt again. So the discovery about Edwin Hubble, about the universe expanding. Do y'all remember what that data was? That implied that the universe was expanding? He was able to tell by looking through his microscope, not microscope, telescope, but it wasn't the Hubble telescope, that's without our space. This is, one he had here on Earth, but he noticed by looking at redshifts that all these galaxies were most of them were receding away from us, and the ones that are further out were receding faster. And so based on that, if you go backwards in time, everything's getting closer and closer to a point in time, which was the Big Bang. And then the background radiation, when they first built the antenna, they were testing it and they kept getting this background stuff, and they thought it was an error or some kind of problem with the antenna. They thought maybe it was the pigeons had pooped all over it. They thought that was the problem. They cleaned it all up and it still kept going. And so finally they made the connection that no, it's out there and it's supposed to be out there. And I'm not sure exactly which scientist kind of made the connection, but since then it's pretty much been widely accepted about the Big Bang. Okay, so last little paragraph there, Catherine.
The Big Bang, as this creation explosion is now called, was first proposed in 1927 by George I don't know how to say that,
Yeah.
a Belgian Catholic priest and scientist. The idea is that the universe was formed by an initial explosion from a single point of all the energy contained in the universe. Within a fraction of a second of this incomprehensible burst of energy, some of the elementary particles released in the explosion, electrons, positrons, neutrinos, and photons, began to condense into the protons and neutrons we associate with ordinary matter. Much of the initial light energy present in the Big Bang persists to this day, and since the universe has been expanding for 13.8 billion years, the wavelengths of the high energy initial radiation have expanded to the much longer wavelengths of the microwave region of the electromagnetic spectrum. This radiation is the CMB.
CMB for cosmic microwave background radiation. Going back to that picture, flip back to 134 for a second. You saw the 13.8 billion years on the far right, and then there's 380,000 years, but like right in the middle, this is not to scale, is it? Right in the middle is 3 minutes. And so like the first half of it is just covering the first 3 minutes. Okay, and there was a lot of changes there. And it goes back to 10 to the negative 32 seconds. And then where it says 0, really as far as they can go back is 10 to the negative 43 seconds. And that's called Planck time. And you can't get a finer resolution basically than 10 to the negative 43 because of the Heisenberg uncertainty principle. And so they can't go back any further than that, which is still pretty close to 0. I mean, that's 0.000 with 40 something zeros, right? So it's pretty tiny amount of time. But all this they've done with math. They've come up with all these things with equations. And let's see, nuclear fusion ends, cosmic background, neutral. Okay, and then the last white line to the right, the last vertical white line says earliest time visible with light. I'm not sure if that's with yeah, I think so. That's that last white line. And so before that, the universe was opaque. You couldn't see anything. And since then, it's become transparent. Now we can see things. And so it was thousands of years before it became that way. And then they show little galaxies and stars there to the right. Okay, so quantization of energy. So Kate, you're next. Gets technical here.
Another essential component to the energy big picture is the discovery that energy is quantized. To provide enough background for you to appreciate this story, we need to bring in the very interesting concept of a black body. Consider the pupil of the human eye. Do you know why the pupil is black? The pupil is a hole in the front of your eye where light enters. The reason pupils are black is that light enters the pupil and then absorbed by the retina. None of the light that enters the eye finds its way back out. The blackness is simply the absence of light. A pinhole in the top of a shoebox does the same thing. It always appears black because any light entering the hole bounces around inside the box until it is absorbed and doesn't come back out. A black body is a hypothetical object that absorbs radiant energy perfectly and thus allows appears black at ordinary temperatures. Now, no object can constantly absorb energy without radiating energy away from itself. In fact, any object in thermal equilibrium with its environment will radiate energy at the same rate that it absorbs energy. A black body does this perfectly at all wavelengths, so it is a perfect absorber and perfect emitter of radiant energy.
Okay, so that little paragraph about a black body is pretty important. And the first thing it mentions is that it's a hypothetical object. There's no perfect, or there's no real world perfect black body, but scientists propose it. And based on what they say there, would you say that you as a human being, your body, are you in thermal equilibrium? Hopefully not, because if you are in thermal equilibrium, that probably means you're dead. So you're radiating more energy than you're absorbing, okay? But a black body has it just even, okay? And so it's a perfect absorber and a perfect emitter of radiant energy. Okay, one more paragraph, Kate.
If we could lay our hands on a true black body, we would be able to heat it to any temperature and at thermal equilibrium. The energy it absorbed would be perfectly matched by the energy it radiated. The best approximation we have for a black body is a small hole in the side of a metal box. The hole in the box acts like a black body, and since the box is metal, it cannot be heated to high temperatures.
It can be.
It can be heated to high temperatures without being consumed, unlike a shoebox. If we make such a box out of iron, the hole will be black at low temperatures. But as the box is heated to the point where the iron becomes dark red, then cherry red, then white hot, the hole will exhibit the same appearance, dark red, cherry red, and red.
Okay, and so you've seen this when metal gets heated up, you can tell it gets red and that kind of thing, right? The element on the electric burner of your stove, even glass, when you heat it up, will start glowing red. Okay, and so what's interesting is that these colors don't depend on what the material is, whether it's glass or aluminum or iron or whatever other metal you want to think of. It only depends on the temperature. The temperature is what determines the color. So we'll let Kyla start reading.
It turns out that a black body like this actually emits a spectrum of electromagnetic radiation. It depends only on its temperature. Figure 5.2 shows the radiation spectrum for objects at a few different temperatures. Any object heated to 5000 K, which is approximately the surface temperature of the sun, will emit radiation in a distribution of wavelengths that follows the curve shown in the figure for that temperature.
Okay, so I'm going to interrupt you there. So go back to the picture, the little graph. Let's look at that because it's really important when you're talking about energy and how energy was quantized. And a little bit, remember when we got in chemistry, we talked about spectra and every element had its own spectra. This problem right here is what kind of led to that discovery. But anyway, look at the graph. And you see you have those three lines, and one of them is labeled 3000 K, and one of them is 4000 K, and one of them 5000 K, right? See those three different lines? And where is the peak of the 3000 K at? What wavelength?
Around
0.1?
1.
1, yeah, 1.0 wavelength. You see that? That's kind of where the middle of that 3000 hump is, but it's kind of what they call skewed to the right. And then at 4000, the peak is kind of in between 0.5 and 1. So it's a shorter wavelength. And the y-axis is radiant intensity. Okay, look at the units there. W per m squared per nanometer. Whoa. And then as you get to 5000, the peak is even lower. It's just past 0.5. And they show the visible light spectrum there. And you see that at 5000 K, the peak is kind of right in the middle of the visible spectrum, right? And they also mention how the sun, the surface of the sun is about 5000 K. All right, and it's probably because that sun was here when evolution and creatures were developing and all that kind of stuff, that eyes became sensitive to those particular wavelengths because that was the wavelengths that were coming to the earth, right? And if you get higher and higher temperatures, it goes closer and closer to the left as far as the energy is concerned, shorter and shorter wavelengths. And also, when you have all the purple through red together, you see white light, right? And so our sun out in the middle of the day looks white. At 4,000, you have more of you have all of the colors, but you have more of the red and yellow, right? You don't have that much of the purple under the 4,000 curve. And so that light's going to look more reddish. And then the 3,000, you don't have hardly any purple, and there's mostly red and yellow. And so that's going to be real reddish. Okay. And that's why flames, like you see in a Bunsen burner, when they're real orange, they're not that hot. You can run your hand through it. You don't want to hold your hand there, but you can run your hand through it. It's not that hot. But when you get the burner up to a blue flame, that's all the way over to the blue side of that spectrum. So the temperature is much higher there, and that would be dangerous. Okay, so I wanted you to look at that, and look at the dotted line they have there too. Prediction of classical theory at 5,000 K. And so if they use the math that they had before about 1900, the year 1900, then if they use the math, they get that dotted line instead of the actual line for 5,000 K, but they measured and they knew what the actual curve looked like, but the calculated curve was different. So they didn't know what was wrong. And so I think he gets into that in the next page. So we'll let you keep going. You're on the next page at the top.
As you can see, at 5,000 K, a large portion of the radiation is in the visible spectrum, which is why a body at this temperature appears white. It is radiating throughout the visible spectrum, as well as in the UV and IR portions of the electromagnetic spectrum. At 4,000 K, the peak of the emission spectrum is in the red region of the visible spectrum. So an object at that temperature possesses a reddish hue. As an aside, you may have heard photographers or artists who use lighting refer to the color temperature of different lighting sources. The color temperature is the color a black body exhibits at a given temperature. Color temperatures above 5,000 K are said to be cool because the white light develops bluish tint above 5,000 K. In figure 5.2, you can see that the higher temperatures, the peak of the spectral distribution curve moves towards the blue region of the visible spectrum. Color temperatures in the 2,700 to 3,000 K range are said to be warm because of their distinct yellow or reddish hue. These hues are illustrated by 3 different types of lamps in figure 5.3. Okay, so stop there. It's interesting because artists and other people, they talk about blue being a cool temperature and red being a warm temperature. And that's just the opposite of what they really are in real life. In real life, when something gets blue hot, blue, that hot is really, really hot, and red is not very hot. So it's kind of just the opposite. Like when you look at a faucet and you can have the hot water or the cold water, they'll always have a red dot with the hot and a blue dot with the cold. And it's just the opposite with these temperatures. When you get hotter, it becomes bluer, and cooler is redder. And look at the light bulbs there on page 138. Can you see the difference of colors? It shows better in the little glow around the outside of the bulb. You see kind of a bluish one around the twirly one there at 5,500 K, the 13-watt fluorescent, it's kind of a bluish glow. In the 3,500, it's kind of a more yellowish glow. And then the 2,700, it says about 27. At first it looks like negative, but it says about 27 K. And so it's kind of a reddish glow. And you can notice that with the lights in this room. Do you see different colors? About how many? Like about 3 or 4 different colors, right? And when Eric was in here changing the one that had been flickering, which one? I think it was that one right above Catherine.
I said, well, look, that color is different than just about all the other lights. And he goes, yeah, this is an old building and these lights will last for a long time and have to be replaced over time. And during that time, the standards have changed, the manufacturers change, what they order changes. And so you end up with this. But when we get into the new building, they're all going to be, I think, kind of like this more whitish. I'm not sure exactly, but it's what is supposed to be best with the latest research. But anyway, okay, we will let.
In the 19th century, physicists were quite puzzled by the complete mismatch between the actual spectrum of radiation emitted by the black body, the hole in the iron box, and the prediction of what the spectrum should be based on the best models of classical physics. Looking back at figure 5.2, the dashed curve on the right side of the graph is prediction from the classical physics of radiation spectrum of a black body. If you mentally extrapolate the curves to the right for longer wavelengths, you can see that at wavelengths above 3000 nanometers, or the classical prediction approaches the actual emission curves. For shorter wavelengths, the classical curve increases without limit.
Okay, so let's look at that real quick. Going back to flip the page back. So if you go way to the right, the very right end of that, and you see how the dotted line is kind of similar to the darker lines. I mean, they're pretty close, especially as you get right to 3.0 there. It's pretty close, which is still 3 micrometers. That's still 300. No, it's not invisible. But anyway, as you get further left, it really varies from the actual data quite a bit. Okay, keep going.
Classical physics actually predicts that the energy radiating from a black body approaches infinity as the classical prediction fails to show, is that the emission curves reach zero. Obviously, such a prediction cannot be correct. The reality which the classical prediction fails to show is that the emission curves reach a peak and then fall off to approximately zero below 200 nanometers or so. The failure of prediction to match measurement became known to more sober scientists as the black body problem, and to more excitable scientists as ultraviolet catastrophe. This problem was one of the major conundrums facing physicists in 1899 as the 19th century came to a close. In 1900, German scientist Max
Planck,
shown in figure 5.4, inadvertently stumbled onto a solution to the problem that would end revolutionizing the world of physics. Planck developed an equation that matched the measured spectral curves very well and began trying also to develop a theoretical basis for the equation. Out of sheer desperation, he decided as a temporary expedient to assume that the emitted energy was not a continuous quantity, but was divided into small lumps or packets, quanta. He proposed that the radiant energy emitted by a single atom in a given material was related to the frequency of the light by this equation, now known as the Planck relation, E equals hf.
Mm-hmm. Okay, keep going.
In this equation, E is the energy of the individual packet or quantum of electromagnetic radiation. F is the frequency of the radiation, and H is a constant, now known as the Planck constant.
You don't have to say that. So y'all remember that from chemistry, Planck constant. And do you remember how we changed it in chemistry to be E equals HV over lambda? Remember that? So V over lambda, the same thing as the frequency. Yeah. Okay, so keep reading.
Planck further proposed, again, just as an expedient for calculations, not as physical reality, that all energy was emitted by atoms in integer multiples of the fundamental quantity hf. The Planck constant is an extremely small number, and accordingly, a quantum of energy is an extremely small amount of energy. The exciting conclusion to this drama, which was actually no conclusion at all, but the birth of quantum physics, occurred in 1905. That year, German scientist Albert Einstein, shown in figure 5.5, boldly published a paper demonstrating that what Planck had regarded as a computational formalism was actual reality. Energy was quantized. Energy was not a continuously variable quantity at all, but only existed in quanta, small packets or lumps, each possessing an amount of energy that was a multiple of hf. The significance of these discoveries cannot be overstated. Physics was changed fundamentally and forever. Quantum physics is now used for scientific modeling of atomic scale systems. However, when hf is very small compared to the energies involved, classical physics still works well.
Which is what we're going to use. Okay, so he's given some background, but you wouldn't really get into all of that science until you get into college or even grad school. But it's really pretty fascinating. And they have the picture of Einstein there, but he was just a young man. There he's kind of old and white haired, but he was, a young man when he discovered all this. Okay, so that's all we're going to read. That's just kind of the background, the big picture of energy. And so what I want you to do now is we're going to answer exercises 1 through 5 over on page. Back here somewhere, hang on. Page 163. Okay, and you'll find those answers in what we just read. And I want you to go through 1 through 5, but also if you flip back to the beginning of the chapter where the objectives are, objective number 4 says, describe the roles of Max Planck and Albert Einstein in the discovery of the quantization of energy. So I want you to do that as well. So exercises 1 through 5 and then objective 4. That's page. And then 35. So we'll just spend the rest of the period working on these questions. And if you have any problems finding anything or any other questions about it, let me know. And that includes people online as well. And online guys, y'all are welcome to use the chat, or you can unmute and ask questions either way. How many of y'all got to number 5 yet? Can you go up to the front and explain what they're just talking about there? Because that's really the one that they don't. Number 5 says, discuss why steel can be heated to white hot but not to blue hot. And the reason, if you look back at that chart, is because whenever it has a peak up in the visible, anywhere in the visible spectrum, it's going to have all the colors, right? And all the colors combine, even though there's blue in there, all the colors are combining to give the white light. But there are stars that are out in the universe that are even hotter, so that their peak goes completely, almost all the way into the ultraviolet range. And those stars actually do look blue. But steel, with the temperatures we can reach here on Earth, you're going to have all the colors. So it gives you the combination of all the colors, which is white. Yeah, and then if you're done, you can just turn it in. Yes, sir.
Mrs. Belcher. Mrs. Belcher. Mrs. Belcher.
Ava had a good question on there. She was wondering what the K stood for on the chart. Anybody remember? The unit for temperature. You know the temperature, what the unit is? Kelvin, remember Kelvin? Yeah, it's the absolute temperature Kelvin. You know what room temperature is approximately in Kelvin? About 300, a little less.
It's in the term all the colors.
Right.
Okay.
Yeah, when you mix blue with all the other colors, you get white. If you don't finish in class, try to get it finished before tomorrow. Remember the due date. We're gonna read some more into the next section and answer some more questions. Yeah, due tomorrow. The school time and real time are way off again. The real time is like, it's only like 9:21 instead of 9:25. Yeah. The clocks in the room are off, and that one is too. If there's a variation between the real time and clock time, y'all can get to a stopping point and get excused to your next class. And for those of you online, if you're in calculus, you can just stay on the meeting room and not have to calculate. So I'll see you later, Cameron. If you have any questions on the questions, you can text or email me before tomorrow.
Later.
Mrs. Belcher. Mrs. Belcher. I have a question.
Mrs. Belcher, I'm gonna leave because I'm not in this math class.
Not paying attention.
Um,
Just leave.
bye, guys.
Bye, Cameron. Mrs. Belcher, I have a question. Mrs. Belcher. Mrs. Belcher. What is it?
I don't like this.
Being online?
Yep.
She won't answer my questions.
She
She's
can't
ignoring.
hear.
She's ignoring me.
No, she's not. Because like, when I tried to like tell her about you being in the waiting room, she couldn't hear me at all. So I don't know.
So, how's life, guys?
Good. How's it going, Corona Brian?
You know, that's my nickname around the house now. I'm
Really?
COVID boy. Yeah, that's what they call me now.
COVID
That
boy.
sucks.
He's the infectee.
Are your sisters at school, or are they staying
they're
home
here.
too?
Yeah, they're here.
Yeah, Jerry went to school, so we'll see how that goes. But he's also in the middle school, so I think he should be fine.
Yeah.
Yeah.
Is this the right book? Mrs. Belcher, I have a question. I have a question. I'm going to ask it.
Can we get a rip for Spanish?
Yeah, Kate's gonna be the only one there, right?
Or Kate.
If only she could hear us now.
I know.
Kate.
If you
What
remember
if we screamed
before
really
Camp
loudly?
Eagle,
I think she could hear
y'all
us.
Wait.
remember?
Just wave.
We were talking about derivatives of inverse trig functions,
Why is that a thing?
like tangent to the -1. So go ahead and open your books to section 4.5, page 146. We'll kind of refresh our memory a little bit. And in a minute, we're going to talk about which ones we already did on the board, because I know we did some of them. And I want to be able to list them so we can give you credit for it. So 146, the first thing they had on page 146, 147, and a little bit of 148 was just reminding you what an inverse function is. Remember that? Talked about how a function is inverse or reflections of each other over the y = x line. And their x and y coordinates are switched, right? And you can tell if a function is a function or an equation is a function if it passes the vertical line test. And you can tell if its inverse is a function if it passes the horizontal line test. Remember that? okay? And in order for all the trig functions to have inverse functions, we had to constrain their ranges. In other words, if we looked at the inverse from negative infinity to infinity, the inverse would not be a function. So on page 149, it shows how we just are using a certain range, a certain, not a certain domain so much, because the domain can still go from negative infinity to infinity on some of them, but the range is restrained from either negative pi over 2 to pi over 2 or from 1 to pi. Okay, and you see those on page 149? Okay, and then they give you those ranges on page in the little chart. And then on page 150 was the fun part where we got to derive the derivatives of these inverse functions using a little bit of geometry. Remember making the little triangle in the first quadrant and going through and using implicit derivation? And y'all did a lot of those on the board. And then the actual derivatives are on page 151. So I know that we did not do the Q's when we were here on the board. And all you have to do on the Q's, Q1 through Q6, is copy down what the derivatives are from the little chart there. And they're also on your formula sheet. And then on Q7 through Q10, you're looking at a little graph there, and it wants the derivative at 1, 3, 4, and 6. And so what would you do to figure out the derivative at those points? Estimate the slope of the tangent line, right? And yet, yeah, especially when you get to 4 and 6, you can actually find the actual slope because it's a straight line. But on numbers Q7 and Q8, you'll have to estimate the slope of the tangent line. And I do not think we did 1 or 3 because those involved just getting them on your grapher and copying what the graph looked like. And that's a little tricky for cosecant because you don't have an inverse cosecant button on your calculator. And so you have to type in 1 over sine of x for y1, 1 over sine of x to get that. Cosecant. But you want the inverse. So you'd have to do, yeah, 1 over sine to the negative 1. Okay, and then we didn't do 5 or 7. I think what we did was, and y'all can let me know if you disagree, but I think we did 9 and 11. That was where you had to actually do the derivatives. So I think y'all did several of those. And then we started going through some of the other ones, I believe. Do you remember doing 13 and on? No, not really. You had to use chain rule. It'd probably be good to go back and do them again anyway, if you did, even if we didn't do them. So I'll give you credit for DOB on 9 and 11 if you want to write that down. But if you don't remember doing those derivations, you might want to go back and do them again anyway. Although I think 9 is, no, they give an example with tangent and they give an example with inverse secant. They don't have inverse sine. And if you want to see me go through one of those derivations again, I'd be glad to do that. Does that mean, yeah, you understand, or yeah, you want me to? You understand, okay. Maybe later. Okay, well, let me know. So if you want to work on the board, you can, those of you that are here, or you can work on your own paper. And if you work on the board, I'll help you out.
What's the actual assignment? Mrs. Boucher.
Just emailed it.
doing? Are we just doing?
Oh, I'm sorry. Yeah, we're doing the Qs. And 1 through 25 odd. Double check that. Yes. Go to the dark side. Is that to the light side? Forward. Oh. And this one's not too bad.
Okay, so on the Q's, you just have to find the derivative.
Yeah, which is just listed on there.
Oh,
In this case, it's these guys. Huh? So they have ddx and they have just the prime notation. The prime is the same thing as the d over dx. Does that make sense?
yes.
Okay, so it'd be this one. Wait, derivative of, oh no, it is right, you're right, it's the derivative of sine.
Okay.
So not the inverse, but the actual,
Okay.
the original one. So these are derivatives of the original functions, not the inverse original. And hopefully you can do those from memory, a lot of them. No? I think that's some.
Well, yeah.
Yeah.
Do you want to check it or you can?
Yeah, I'll check it, that's good. And then you can,
Do you want to check it?
How do you get Q's?
Well, because like, it's not,
right, and so it looks like part of a circle, doesn't it?
yes.
And so at the top of a circle, you're gonna have a tangent line that's horizontal, but the side, like at 1, that's the side of the circle, is gonna have an infinite, straight line, vertical. And so the derivative would be undefined. So the slope is undefined. Does that make sense? Six, yeah. 1. Okay, so Ava, I looked at your Qs. Can you hear me? Yeah. So you got the Q7 and Q8 switched. Because on Q7, the slope would be vertical, which would be undefined. And then at Q8, you're going to have the slope that's going to be 0 because it's horizontal. And then on Q9, I think you just need a negative sign. It's like the slope is negative 1. And then 10's right.
Well, because.
see what slope like. Also, Ava, you said that you forgot what to do when there's no slope like 8, but they don't ask for the slope at 8, do they?
Because, hold on 1 second. They're asking for the derivative of it, right? Which is just
Q8?
the slope.
Or
Yeah, in
X
Q-
equals 8. I can't hear you.
In Q8,
I can't hear you. You're not muted?
no. My mic is on.
Get something on my side.
That's all we do, just.
Can anybody else talk? I don't think I've heard. Brian, can I hear you? If you
You
unmute?
can't hear us.
Yeah, I don't hear Lewis either.
We can hear each other.
No, that's not it.
I think we're just graphing it.
You can hear each other and you can hear me, right? But we can't hear you. Oh, well. I'll try to figure it out. Meanwhile, what did you mean by 8?
By 8? Okay.
Can you type it in as a, chat thing?
Oh, no.
I'll text you. Okay, great. Are you on then? Okay. Yes.
I just need you to check my.
Okay, I think it's -1, right? Because it's gonna,
Is Kirsty can't?
Oh, cause it's going down.
and then 0 can't get. We need to look at, yeah.
Okay, and then for 1, we're just re-drawing the graph, so it would just be like.
Or the inverse cosine. Yeah, so it looks like that, but actually
What if you
compare
want
that to what they have here. Okay, so it should go all the way down to the x-axis, you know, and up to where pi is.
I wonder if I zoom.
It's maybe, it's probably a resolution thing. Yeah. So be aware that your calculator may not show every little thing, but because it should really look. Okay. What, is that number 1?
Yes.
A straight line?
Well, you know, it's just some curves.
Did you?
Well, yes, I did, but it looked straight to me.
Well, that's fine, 'cause this is 1 over, because they're doing that one, okay, but if we did.
Do we need radian or degree mode?
Radius.
Thank you.
What? Oh, I flipped.
Okay, so we did second cosine of n x. It does look kind of straight, okay? So if, say we zoomed in, we didn't use that.
Look at that curve.
Yeah, so it's kind of, you should be comparing these to the ones on your book. On page 149. This is what it looks like here. Look at that. It should look kind of like that. And you see how this doesn't look like it goes all the way down to the x-axis? That's just because of the resolution. It does actually.
Oh,
Okay, your calculator doesn't have the resolution. I bet the newer ones that have the colored lines probably do. Yeah, so it kind of looks like what Captain has there. So I was just getting y'all familiar with those.
no, I think it's because it just wants to be that.
Because it's flipped over the,
Hmm.
and it's like, and then it went like that. And it's not, it's not vertical anymore. Yeah. I was gonna say that. Did we just put them right?
Okay, y'all listen up. So look back at Q8. Ava was asking this. Q8 is, you're looking for the derivative when x is 3. And I was just looking at it at the top of the circle, so that would have a slope of 0. But she says, well, if you come from one side, it's 0, but if you come from the other side, it's -1, right? And since it's different on each side of 3, it's actually undefined for Q8. Okay, thanks, Ava, for pointing that out. That is correct.
These will just cancel out, right?
Yeah. Go ahead and see if you can type it into your calculator and see if it comes out to that. And 5. Okay, and Catherine, I like how you mentioned number 5. And which one is it for the cotangent? You said so it would be continuous, but and it is continuous, but that's not the reason they use that range. So on number 5, they changed it from 0 to pi because they want it to be a function. If they did the other one, could you have this other one up here? They would do this and this, if they went from -pi to -pi/2 to pi/2.
Oh, then it wouldn't really be.
Well, it might be, I guess if that's pi/2, you have that and that, and it would still be a function. And in fact, I think some calculators do that part from -pi/2 to pi/2. So I guess I'm gonna go with your continuous after all.
Okay.
I was thinking that it would make it not a function.
For 13 through the rest,
Mhm.
do we just plug in 4x for x?
You're gonna, yes, you do, and then use a chain rule. That's not the same.
You just plug in,
Ah,
you take the,
okay, let me get my calculator.
and then you plug in 4x. Yeah, you put 4x. What was the square root of the difference? That's what I have to do.
Okay, so,
And then we can do the chain times the 200. Oh, so
okay, so Ava, Get the mic over here. So based on what you put in your calculator, you had cosine X, all of that raised to the -1, and it gave you that weird graph. That's because what you did, you put the reciprocal of cosine, which is secant, and it did graph the secant curve. But if you're supposed to do the inverse cosine, you use the second and then the cosine button. Right above the cosine button is inverse cosine. And so when you go to y equals, it looks like that. And then you get a graph. I use the windows that they have on page, well, similar to the windows that they have on page 149. And so it looks like that. Yeah. Okay. On which one?
13.
13. Okay. And they can see me here. I've had the camera on you all this whole time.
Oh, that's fun.
Like that, right? So 13. Okay, so y prime, you would use this and you'd have 1 over the square root of 1 minus, and in parentheses, you'd put your 4x. And then that would be squared because you're doing this one right here. Yeah. Okay, times, because it's chain rule, the derivative of 4x, which is just 4. Okay, so then I can put that 4 on top here and have 4 over the square root of 1 minus, then when you square 4x, you get 16x squared. And they may have something weird in the back. Let me check it. 4, 5. Oh, good. Sometimes they simplify weirdly. So I've got number 17. I have the back of the book being incorrect.
What do you have for 17 then?
Huh?
That's my question. What do you have for 17?
It should be 3 over x times the square root of x squared minus 9. Does that make sense? Instead of the 1 on the top, it should have a 3 on the top.
Well, can you help me with 17?
Do it on the board?
Yeah.
Yeah. Right there. Okay, that's not very. I'm going to move it back.
The derivative of e is just e to the whatever, and then you have to take the derivative of that. Which would just be 1/5 times e. I don't think you can simplify the e squared. Okay. That just says
Are you all doing 17? Yeah, got there. Okay.
oh, Well, it's got the number, but who needs to- now I'm saying.
Okay, did you get this, Maddie, when you finished 17?
Yeah.
Okay, that is correct. What they did is they did some more work on it to get that 9 to not have a fraction in the bottom. And so I could tell you how they did that, but you can just leave it like this.
Okay.
Yeah. So you guys, when y'all get to 17, this is the answer. Not what the back of the book has. And you can see how I did it if you want. Let me go over here and.
It's not so bad.
That makes sense.
Yes.
Yeah.
We'll just cancel that out.
Well, this
Because if it
is
has five-
this.
Yes.
Okay, so that's not there anymore, right? If you
No,
put that
no,
there,
no, no.
right. Okay.
Yeah.
Yeah, and then that canceled that, and so you just have that,
And then 3 squares. Okay.
right?
Yeah, yeah.
Y'all got 15 okay?
Yes.
Good. Cotangent.
Well, when it use like a five. What would that be?
Oh, yeah.
Oh, no, I was talking about something. Yeah, this is the answer right here. Yeah.
Okay, so Ava, on your question on number 5, if they could have used, hang on, does that look like that? Nope, it does not. Yeah, I did that completely backwards. They would have had this,
Where's the?
and then this.
Well, so you would just do the same thing with that. You would just go-
So for negative cotangent of x, Ava,
It would just.
in order for it to still be a function, they could have done it something like this, and that would still be considered a function. But what they did was, they said, no, we're going to go ahead and use
It would just be X.
But the whole thing is
from 0 to pi, instead of from negative pi over 2 to pi over 2, we're going to go from 0 to pi because it's a function too, and it's continuous. And so they say that on the bottom of page 148, it says the principal branch, in other words, the one we use for the function, is near the origin, continuous if possible, and positive if there is a choice between two branches. Okay, like here, you've got some negative things too. And so either one of these would have been a function, but they used this one because it's continuous. And that's what they're asking there. Where was it? 5. Explain why the principal branch of the inverse cotangent goes from 0 to pi here to here, rather than negative pi over 2 to pi over 2, because they're making sure it's continuous.
Yeah.
2 inverse sine x times the derivative of inverse sine of x. Yeah, so you did the chain rule.
Yes.
The derivative of the outside times the derivative of the inside. Yeah, and you could put all of this up here if you wanted to and have it in one fraction. You know what I mean? So, you know, that'd be like over 1. In the back of the book, I think they would do that.
Okay.
That's good. You all right?
This is in parentheses now. There's no.
Let me take. Let me see. Okay. So 21. Okay, so this is the actual function, right? And so you've got something raised to the second power. And so the derivative with that, if you had something raised to the second power using the power rule, you would put the 2 down in front and then raise it to the 1. And then you would multiply it by the derivative of the inside, which is this. All right. Okay, and so like if this is y equals that, then y prime would be 2, and then leave all this the same to the 1 power, and then times this right here.
Oh, so you leave this and then it would be times
1 over, yeah. Using the chain rule. That makes sense? Let me erase that because it's just floating there. Okay, and then what they probably do in the back of the book is this is like over 1, and if you multiply straight across, you get 2 times inverse sine of x over the square root of 1 minus x squared.
Oh, I see. And then this one, it said 25, but I got 20, and I don't know.
Because you have to square 5.
Oh, you only square 5. You
Yeah.
don't change this to a 4. You just leave it as a 2.
Well, okay, so if you have 5x squared, so then you distribute this like that, you get 5 squared and x2 plus 2, no, times 2. If it's the power of a power, you multiply.
Oh,
And that's where you
okay.
get 25x to the 4th.
Thank you.
Mhm. Which one? 23, that's what y'all are on? Okay. And this looking back at me. Is it one of those or is it a word problem? One of those. Oh, and it has a surprise. Those are fun, right? E equals x sine inverse x plus 1 minus x squared to the 1/2. So where'd they come up with that, right? Okay, so Lewis, when I get done with 23, I'll go back to 21. Okay, so let me get here where they can. And so this is a product. So we have to use product rule where X is U. I'm gonna just erase that. I don't even like that. And inverse sine is V. And so we're gonna go U prime V plus U V prime, just for this part. And then we'll do this in a minute. Okay, so U prime is just 1. Okay, V is inverse sine X. Ugh. So V prime would be the 1 over square root of X. Okay. And I'm gonna have to continue on over here. So that's just for the first part. Okay, and then for this part, we got to use the chain rule. 1/2 1 minus x squared to the negative 1/2 times 2 times negative 2x. Because the derivative of negative x squared is negative 2x to the 1. Hopefully, is that all showing? Can y'all see that well enough on the board? Not really. You can move it closer. Maybe that'll help. And break it. That's better. Okay. So let's see if we can clean this up a little bit. So we get just inverse sine x there. And here we have x over square root of 1 minus x squared. And then here we're going to have this minus sign I'm going to bring in front, so it'll be negative. And guess what happens when you multiply this 1/2 by the 2? They cancel. Okay, and so we just have x. And what does this raised to the 1/2, negative 1/2 mean? That's the same thing as 1 over the square root. The negative means over, and 1/2 means the square root of 1 minus x squared. And then we still have this x here. So all of this becomes this right here. Because the 2 and then the 1/2 cancel, and then I change the exponent, the fractional exponent to a radical. And then you notice that this and this are opposites. So they cancel. That's the surprise. And so all you're left with is inverse prime x, inverse of sine x, the inverse sine of x. There we go. And that means that if you had to do the integral of this or antiderivative, you would get that. The antiderivative of inverse sine is all of that.
What?
That's terrible, right?
Is that something you're not gonna chop to?
Actually, I don't remember. I don't think we get that far doing the integrals of the inverse trig functions. Yeah, that's pretty ugly. Okay, let me go back to 21. And I'll move this
Okay. I'll take a look.
this way. Hopefully that can,
Okay, because.
yeah, okay.
So would it be,
The opposite is, the opposite is x, and then there's a
Yeah. So here we need to use the chain rule.
Fine. Yeah. So, oh, I guess you just put it in there. But no, the theta equals that equation.
13.
So I think it's just another way to say dy over x. You know what I'm saying?
Of X over.
Use the chain rule.
So the derivative of X over 100.
Okay, so on 21, you have to bring the 2 down in front and then raise it to the 1. That's the power rule right there.
No, 'cause
And
you
then
have to-
times the derivative of the inside,
you have to
which is
add it
1
to it.
over
And
square root of 1 minus x squared. And then they would probably put the 2 inverse sine x on the top and the square root of 1 minus x squared on the bottom.
Yeah, x over 100
So that's 21.
times
And does it all
1
show?
over 100, right? You got the
I think so. Okay.
And the
And
original
then
was X.
13.
That's the derivative.
Oh, 13. Okay.
Okay.
Is that going to show up?
Think.
Probably not.
100 over 10,000 times 2. Well, because I multiplied by the derivative of x over 100, which is 1 over 100. And then I took this down and flipped it and multiplied it by the 1, but it's not right for
On
the
13, you're going to use the chain rule. So the derivative of the outside function is 1 over the square root of 1 minus something squared. And whatever you have in this here, the inside, that stays the same. So you just put 4x there. Wherever x goes on the, yeah. Okay, because the derivative of inverse sine is 1 over square root of 1 minus x squared. But instead of x, you have 4x. You put 4x squared. And then times the derivative of the inside. Okay, the derivative of 4x is 4. So then we'll put the 4 on top. And 4x squared, you have to square the 4 and the x. So you get 16x squared. So that's 13.
That's how you did it. I don't know how to do Yes. Okay, remember we did x.
I think 19 is the only one I haven't done.
This is also
Mhm.
help with 25. But we're trying to find the
Okay.
this.
Okay, so you had,
I got that and I plugged it in.
hang on. So did you start out with they had on the A, they had inverse tan of x over 100. Is that what you have?
Yes.
Well, you just didn't show it. Okay. Yeah. And so in B, you're taking the derivative of that, right? Yeah. So d theta dx. Oh, this is t's.
Yeah. So you would flip the 100 and the x since it's.
No, because we're saying like for inverse tan, you would flip adjacent over opposite. So it would be 100 over x instead of. So then the derivative of 100 over x would just be 100. Do you see what I'm saying?
Yes, but
Okay. So inverse.
why didn't we just do it in the first place?
Let's see if I can do the baby steps. So That'll make sense.
What we did was take.
And then you have to put t over 100 here like that, and then times,
1/100.
yeah, which is like, can I erase that? Okay, and so that's the same thing as 1/100 times 1 plus. And then if you square this thing, you get t squared over, and I'm just gonna write 100 squared. Okay, that make sense? Then when I distribute the 100, I get 1/100, and then this 100 cancels one of those 100s. Done, done, like that. So you still get t squared over 100. Is that what they have?
No.
Okay, so they probably didn't like this right here.
They got 100 up here, right?
Yeah.
10,000. 10,000.
So what they did is they multiplied the top and the bottom by 100 to get rid of that. Which I think you can just leave it like that myself. And so then 100 times 100 is 4 zeros. And then here that would cancel and you get t squared like that.
Okay, yeah.
Except they had 10,000.
that's
Yeah.
what they had.
Yeah. So
either
this
way.
would be fine
Okay.
for me. I don't mind a fraction and a fraction. But it's good to know what they're doing so you can tell if yours is the same or not. Okay, I'm going to move this over so you can see. What number was that? 25? 25B?
Yes.
Anybody still need 13 or 21? I can put it back, or you can, well, at some point I'll have the video on YouTube.
Okay.
25. Yeah, and it needs to go down a little. Yeah, there we go. Yeah.
So we just plug 500 into X. Version. So we're saying when this is equal to -1/4. So you just
Let's see what you're doing there.
that would make sense.
Oh, no. So that was an X. They have X and T in here. That was X, and that was X, and then this is still X. And so on until you get down to here. Because you're finding d theta dx. And then that's d theta dx. Now we got to get the d theta dt. Okay, hang on, dt.
I don't think I plugged mine in right. I got 3 points.
Horrible marker.
Oh, so we're gonna have to solve this. Because if this is gonna equal 4, we have to plug it in.
Okay. So y'all got this for d theta dt, right? I mean, d theta dx, sorry. Yes, that's the part 1 of B, okay, for d theta dx. Okay, then if you look over here, and I'm going to take this over here too. So they want you to also find d theta dt. Okay, and so the chain rule. So this thing right here is the chain rule. If you want d theta dt and you have d theta dx, then you need to multiply it by dx dt so that my dx's will cancel. And see how that would work? Okay, so we know d theta dx because we found that it was 100 over 10,000. Well, let's do that other one that was not simplified as much. I liked it better. 1 over 100 plus x squared over 100. Okay, and so dx dt, if you notice in the picture, x is that distance. So distance divided by time is what? What's distance divided by time? Velocity. So how fast is the car going? We don't know, right? We'll just leave this dx dt. And so this is basically, I think, what they want. So I think they're going to give you something for here so you can find the speed of the truck. Yeah. And so when you get to C, it says when the truck is at x equals 500, the officer notes that the angle theta is changing at a rate of d theta to t equals negative 0.04 radians per second. So that equals 1 over 100 plus, and it says x is 500. So we're going to put 500 squared over 100 dx dt. Okay. So you got to get this down to a number, get all that down, and then divide both sides by it so that you get dx dt by itself. And hopefully your answer will end up being feet per second. Yeah, second, feet per second. And then you got to convert that to miles per hour.
Wait, so the answer that we get when we divide, I got this. Maybe.
Yeah, let me just do that to make sure that I get the same thing. So I'm going to start with the 500 and I'm going to square it. And then I'm going to divide by 100. And then I'm going to add 100. And then I'm going to reciprocal that. Whoa, that did not work. Okay, so second. No. I got that. 3.8. Okay.
I got yes, I got that when I put the reciprocal, and then when I divided, I got negative 104.
Oh. 4, 6 times 10 to the negative 4 dx dt. And that can be seen almost. Yeah, and so then you're going to go back. Negative 0.04. Negative 104?
Yeah.
So it looks like he's slowing down, but that's feet per second, right? And then you could go to your, you could do conversion factors, or you could go to your fun sci under your apps, and you could convert it there. So if you go to your apps, and it's either under fun sci or sci tools. Mine was fun sci. Do you have sci tools? Or keep going down because it's alphabetical. There it is. Go back up to fun sci. And then hit another key, and then go to sci tools. And then do unit converter number 2. And we're doing speed, so go, or velocity, go down to number 6. So So first you type in the 104, you don't put negative, 104, and that's feet per second. So then you go over here and hit the feet per second and hit enter. And you want it to go to miles per hour. So you go over to miles per hour and hit enter.
Wait, where's the?
That's miles per hour right here.
Oh, there.
And so, and see, they have an E1 here, which means it's going to be 70.9 miles per hour.
70.9.
Yeah. Or negative in this case.
I don't think that's. Oh, okay.
We got a little bit more.
So Chuck is going to do 4 feet per second, and then which is 71. Yeah.
Okay, and over there. Maddie, Kyla, y'all need any help?
Oh, no.
Great. And if y'all need me to move the camera to another part of the board, I will. We get out at 35, so we still have about 10 minutes.
Catherine, do you just want me to put your name on this?
I was about to say.
Tomorrow, I'm going to give you an open book quiz to work on that covers sections 4.1 up through 4.5, this section. So it's going back and reviewing everything up to this point in chapter 4. And I've emailed the quiz to the virtual people. Do you virtual people all have a way of printing? You can print stuff out? Okay, good. I'm sorry, what, Catherine?
Oh, no, there's
Oh.
still-
And y'all will be able to tune into the live stream chapel. This is mine, I think. Yeah. Do y'all have any more questions? No? Ryan said no. Ava, do you have questions? Lewis, do you have questions? Okay, well, I'm going to go ahead and end the meeting if that's okay with you guys. Yeah, I'll talk to you later. And text me if you have any trouble.